All right, we're going to pick up where we left off. So we are still constructing a confidence interval for population proportion, which again is P. We're not really getting to difference of two proportions quite yet. That's in chapter 10. We should now be able to find that critical value for a population proportion as well. So they're back. Conditions for constructing a confidence interval about a proportion. These are the same conditions that we checked back in chapter 7 for sampling distributions. Now, when checking the conditions for a sampling distribution of p hat, we're checking random, independent, and normality. So our random condition is just stated or it isn't. It's the one condition that if it isn't stated, we would continue. We would say proceed with caution. Stated or proceed with caution. If a bad sample is taken, no amount of math can fix that. So if they tell us about a poor sampling method, like there's undercoverage or some other type of bias, we actually have to throw out the sample and start again. But if they simply don't tell you the process, you would just be like, it's not stated, proceed with caution. So normally they tell you. Independence, that is our 10% condition. And remember, the reason why we calculate this is why we check this condition is in order to calculate standard deviation. That's the purpose of checking this condition. And the way we check it is we check that 10n is less than or equal to the population. So we're making sure that the sample size is not too large compared to the population. Our normality condition, and the reason we check normality is so that we know the shape of the distribution of sampling distribution of p hat so that we can use this Z star. So back in chapter 7, we found probabilities, and really we're not saying the word probability when we do this, but we are using the normal curve to find our Z star, right? Because we used inverse norm. So we have to know that this distribution is normal, and the way we check is called large counts. So recall from chapter 7, for large counts, you need to show 10 successes and 10 failures. At least, right? So you need greater than or equal to 10 successes and failures. So you check NP is greater than or equal to 10, and N1 minus P is greater than or equal to 10. Now, in this case, we don't have a P. We have to use our P hat. And our X, which we'll get to in a moment, our X is our N times P hat. So if 31 of 50 in the sample do have or are taking AP classes or something like that, that would be our number of successes. So our N times P hat would just equal that X, 34. All right. Recall, our confidence interval for proportion says statistic plus or minus critical value times standard deviation, where our statistic or point estimate is P hat, our critical value is Z star, and our standard deviation is P hat 1 minus P hat over N, and we take the square root. We're also going to learn today how to use our calculator function to calculate or construct confidence intervals, which is super fast. We're going to do at least one more by hand, though, and then I'll show you how to use the calculator. All right. In a simple random survey, note they told us, so in a moment when we check conditions, our random, independent, and normality, they did state that just now. It was stated. They told us that it's a simple random sample of 3,110 U.S. adults. So I'm going to go ahead and write that down. That's my sample size. N equals 3,110. Out of those 3,110 U.S. adults, 1,435 say they have started paying bills online in the last year. That's our X, our number of successes out of our sample size. Construct a 98% confidence interval. So our confidence level is 98%, which I'm going to go ahead and write that as a decimal, 0.98. Construct a confidence interval for the population proportion of U.S. adults that started paying bills online in the last year and interpret your result. All right, so the first thing we're going to do is we're going to find our P hat. Well, P hat is just X over N, which is 1,435 over 3,110. Which is 0.46 about. There we go. So there's our P hat. And in the end, we're wanting to get p hat plus or minus. We're going to have to calculate this z star. So one of our steps is going to have to be to do this. And we have to calculate our standard deviation, which this is our margin of error. So in a moment when they ask us, just as a reminder, our margin of error is simply the product of these two things, our critical value and our standard deviation. All right, so found the point estimate. We did it. Check our conditions. Random is stated. Now for independence, that's our 10% condition. So we're going to go 10 times n, and our n is 3,110. 10 times 3,110 is 31,100. There we go. And that has to be less than or equal to the population. Well, let's see if that's reasonable. What is our population? So our population is U.S. adults. So our population, U.S. adults. So does it seem reasonable that there are more than 31,100 U.S. adults? Yes, there are more than 31,100 U.S. adults. So we can continue. That allows us to be able to use this formula to calculate standard deviation. But we still need to check normality so that we can use inverse norm, the normal curve, to calculate critical value. So our normality condition is NP is greater than or equal to 10, and you have to have both. N1 minus P has to be greater than or equal to 10. But we don't have P, we have P hat. Now you could, this is what I was saying a moment ago, you could literally go N3110 times 0.46, but I actually know what that's going to be. It's going to be 1,435. Now, if you typed it in, you wouldn't get exactly 1,435 because of rounding. But then that is definitely greater than or equal to 10. You have to do it for both those. So then you're going to have 3,100 or 3,110 and then times 0.54. Which is about 1,675. Which again is greater than or equal to 10. So we are good. And I'll answer your question because I can edit it in a minute.
I was just going to turn into
you can just pop it right in.
Is what we're supposed to do? Just like look at the test and then do? Okay.
Yeah.
I forgot to put my name on it, so.
That's okay. Yeah, I have a, there you are.
Thank you.
You are so welcome. All right, so now when it's time to find that critical value Z star. So remember our process for finding Z star is that we're going to use inverse norm, but we have to give area to the left. So, and to do that, you're going to go 1 minus your C, which is 0.98. Thank you. Divided by 2, which gives us 0.02, divided by 2, which is 0.01. So in my calculator, I'm going to go second bars to get to inverse norm. And my area to the left is 0.01. And I get 2.33. I'm going to round my 100 there. So 2.33 is my Z star. Now I'm going to find the standard deviation. I'm going to come over here. Well, I guess there's still room here. So we're going to go standard deviation of the sampling distribution of P hat, which would also be known as standard error in this case because we're using P hat instead of P. It's going to be the square root of our P, 0.46, times 1 minus P, 0.54, over our sample size, which is 3,110. I'm going to type that in. Oops. So I have 0.46, 0.54, and my sample size of 3,110. And I got 0.009. 0.009. Now it asks us to find the margin of error. I remember that our margin of error is simply our Z star times our standard deviation. So we're going to go Z star 2.33 times 0.009. And I actually, let's see here, 2.33 times, I'm just going to scroll up actually. I don't like to use intermediate rounding very much. So we're going to go boop, just grab that guy. And I get 0.02, and I'll round to the 1,000th again. So we'll go 0.021. 0.021. So now that we have our margin of error, we're able to calculate or construct our confidence interval. So we're going to have, our interval will look like this. And so we're going to go P hat, which is 0.46, We're going to subtract our margin of error, which is 0.021. And then for this value, we're going to take 0.46 and we're going to add 0.021. And I just like to scroll up. So I'm going to go 0.46 minus this value, and I get 0.439. And now I'm going to add. And I get 0.48. I'm going to round to the thousandth, so 1. There we go. And then it says interpret this interval in context. So when we're interpreting this interval in context, we're going to say we are 98%. We are 98% confident that the true, let's see what our parameter is this time, the true proportion of U.S. adults that started paying bills online this last year. The true proportion of U.S. adults that started paying bills online. Very good. Awesome. That started paying bills online is between 0.439 and 0.481. There we go. All right. Let's do one more by hand and then we'll do them both on the calculator real fast. All right, one more. Get really good at this. In a recent Gallup poll, 39% of the 5,914, so that gives us our 39% is going to be our p hat of our selected U.S. adults. So that means our n is going to be 5,914. Construct a 90% confidence interval. I'm going to go ahead and write that as a decimal. And we're going to be constructing an interval to estimate the population proportion of U.S. adults that claim they've seen a ghost. All right. So the point estimate p hat, they actually just gave it to us, 0.39. Check conditions, random, independent, normality. Random, they told us. It's stated. Check. Independence, 10 times n, 5,914. Are you sure? You can, because I can edit the video. Are you okay?
I thought it was a piece of paper in there, but I didn't.
Okay, you're good. All right, so 10 times 5,914 is 59140, and that needs to be less than or equal to, again, we're U.S. adults. There are a lot of U.S. adults, so more than 59,140, so we're good. Normality, I need to check that NP, so 5914 times P, 0.39. So I'm going to type that in. 5914 times 0.39, which is 2,306. 2,306, and that is greater than 10. And then I'll do the same thing in 5914 times 1 minus that, so 0.61. I'm just going to come up here and grab this guy, 0.61.
Okay. The reason I thought this was a class.
You're good. You're welcome. Okay, so we have 3,607. 3,607, actually 0.54, but either way, it is way more than 10. Check, check. More than 10. Check, check. So we're good. We can continue on. I'm allowed to calculate my standard deviation. I can use the normal curve to calculate Z star. Okay, so now to calculate Z star, it's going to be inverse norm. And then we're going to give area in the tail. So my Z star is going to equal inverse norm. And our area in the tail is always 1 minus C, 1 minus 0.9 divided by 2, which is 0.1 divided by 2, which is 0.05. So that's what we're going to type in our calculator. So we're going to go inverse norm, 0.05, and we get 1.64. For our standard deviation, that's going to be p hat, 0.39. 1 minus p hat, 0.61 over n, 5914. So again, we'll type that in. So we're going to go standard deviation, 0.39 times 0.61 divided by 5,914. And I get 0.006. Now find the margin of error. Margin of error is simply z star times standard deviation. So I multiply these two guys together. So I'll get 1.64 times, and I don't like to intermediately round, so I'm going to come up and grab this guy. 0.010. Construct a 90% confidence interval. So I'm going to go, my lower value will be p hat 0.39 minus 0.01, which is 0.38. And our upper value will be 0.39 plus our margin of error of 0.01, which is 0.4. Now we're going to interpret this interval in context. So we'll say, we are 90% confident that the true. And proportion of, notice how I underline this part at the beginning. That helps us when we come down here. That the true proportion of U.S. adults say they've seen a ghost, is between 0.38 and 0.4. That's a lot, actually. So between 38% and 40%, according to this study. Okay, it says a newspaper article claims that over 50% of U.S. adults have seen a ghost. Use your result to comment on this claim. So this is the question that we ask ourselves. Is 0.5 in this interval? This is our interval of plausible values, and 0.5 is not in here. From 0.38 to 0.4, 0.5 is way above this. So we would say, use your results to comment on this claim. This newspaper article claim is not supported. By our result. Because 0.5 is well above the interval of plausible values. Or you could say something like, even simpler, no, because 0.5 is not in our interval. I might like the simpler better, but I do want you to be thinking about this. So what is our interval? It's an interval of plausible values. So a simpler answer might just be like, no, because 0.5 is not in our 90% confidence interval. It is not in there. So if it's in there, we would have said, yes, 0.5 is in our confidence interval. So that's a reasonable or plausible value. But if it's not in there, then we would say, no, we do not believe that. It's not in our interval. All right, so now I'm going to show you really quickly how we could have done this in our calculator. So in your calculator, and it does give you in the notes here how to get to it. So you're going to go stat, you're going to go over to test, and then you're going to go way down to 1 proportion z interval. And it's actually A in your calculator. So I will take you there. So you're going to go stat, scroll over to test. You're going to scroll down way, way, way down. And notice the things that they're asking you for, X, N, and C, which it does tell you right here in your notes. So X is the number of successes, N is your sample size, and C is your confidence level. So for this first problem, notice they actually give us all of those things. I don't have to do any extra work. So had I been doing it using my calculator function, I would simply type in for X is 1435. My N was 3,110, and my confidence level was 0.98. If you type in a whole number like 98%, it'll give you an error message. You have to record your sea level as a decimal. And there is our window. And look, like we're a tiny bit off because we rounded some along the way, and they did not do that same rounding here, but we're very close. So we have 0.44 and 0.81, so super close there. But this would be more exact than our by hand. Let's do this one. In our calculator, notice here, we have our N, we have our C, but we don't have our X, and we have to have that. We actually already calculated it down here when we said 0.39 times 59.1, but if you are given a P hat and not your X, you have to, they just rounded to get their P hat, but to get this, we know that P hat equals X over N. So if you imagine solving for X, you would multiply both sides by N, and so you would get N P hat equals X. So that's how we would solve for X. So that's what we're going to do. We're just going to multiply N 5914 times 0.39. And notice that we have a decimal. Your calculator will not let you use a decimal for X. So you're going to need to round. Typically, when it's a person, we always round up, even if it's 0.4. So I'm going to call our X to 2,307. Now, because they rounded for us to be able to do this, our answers aren't going to be perfectly aligned with our by hand estimate, but it'll be close. So I'm going to use 2,307. So I'm going to go to stat, go over to test, and I'm going to scroll way down to A. This time my N is 5914. My N, X first. 2,307. N is 5914. It's kind of nice that I made that mistake. Be careful there. If your N is bigger than X, like you just put them in the wrong spot, again, it'll give you an error message, because can you really choose 5,914 of 2,307? No, that doesn't make sense. So if you get them flipped, it'll give you an error message. And we want to make sure that we change our confidence level to 0.9. There we go. Again, really very close. So ours is a rounded value, but notice 0.379, so that rounds to 0.38, and our 0.4. We're going to do the next problem, but let's not round this time. This time, let's not do it by hand. We're just going to use our calculator. So this time, I'm not going to do any of this. I'm not going to do any of this. I am just going to use my calculate and interpret, and then is it plausible? I'm just going to do that. Okay, so let's read through. Well, I will check conditions, but I'm not going to calculate by hand. Mrs. Smith's class took an SRS of 102 pennies, so our N equals 102, from a large collection of pennies, and discovered that 57 of them were more than 10 years old. That's our X, 57. Calculate and interpret a 99% confidence interval. I have to write that as a decimal. All right, and let P be the true proportion of pennies in the collection that are more than 10 years old. Let's check our conditions: random, independent, and normality. Random, they told us, SRS, stated. Check, check. Independence, so we have 10 times N equals 1,020. It has to be less than or equal to our population. It does say a very large collection. Population, large collection. And we're going to assume that that large collection means that they have more than $10 worth of pennies in it. So we think this seems reasonable. For normality, we have to know that NP is greater than or equal to 10, and N1 minus P is greater than or equal to 10. Well, I know my successes were actually 57. And that is greater than 10. So I'm good there. And I can actually find my failures by subtracting this, or you could multiply out, but it's the same idea. If I had 57 that were more than 10 years old, well, then 102 minus 57, that's how many that were not older than 10 years old, 45. So 45 is also greater than or equal to 10. So we're good. Now we're ready to type this in our calculator. So we're going to go stat, go over to test, down, 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 way down to A. And we have our X is 57. Our N is 102. Our confidence level is 0.99. And there's our interval. So I'm going to go ahead and come right down and write it. So we have 0.432 and 0.685. Oh my gosh, that was so much faster, right? Okay, so now that we have that information, let's interpret and evaluate our question down here. So it says, interpret the interval in context. This should sound the same every time. We are C% confident that the true parameter is between blank and blank every time. We are 99% confident that the true, and this time we're interested in the true proportion of pennies in the collection that are more than 10 years old. The true proportion of pennies in the collection older than 10 years old is between 0.432 and 0.685. And some people like to write these in percentages. You totally could. It's between 43.2% and 68.5%. Is it plausible that exactly 60% of the pennies in the collection are more than 10 years old? We look at our interval and we say, is 0.6 in this range? Could 0.6 be our true proportion? And the answer is yes, it could, because it's in there. So we could say yes, because 0.6 is in the 99% confidence interval. It's listed as one of our plausible values. Now, that doesn't mean that 0.6 is the exact proportion, but it's plausible that it could be exactly 60%. So if the claim was like, so-and-so claims that 60% of the pennies in the collection are more than 10 years old, that would be reasonable. 0.6 is in our interval, so it is a plausible value. That is all. You can do your practice now. Happy times.